Hello, everybody, and welcome to episode 5 of Building with Blitz. We are going to dive into Mechanics 101. So, this is going to be covering topics from a undergraduate Mechanics of Solids or Mechanics of Materials course, kind of the basic topic intro of what's going on. So, let's go ahead and get started. So, why should we care? I will say I did upgrade the PowerPoints for this video from my friend Mr. Claude helped me kind of get these graphics together. So let's see what's going on there. So the internal forces are kind of the engine behind all structural design criteria and ideas that we're using, whether it be yield stress, strain limitations from deflection criteria, fracture stresses. This is kind of related to concrete and some ultimate fracture stress or ultimate stress capacities and steel members, like steel connections and stuff like that. So what we're doing here is taking a look at what is going on kind of inside the structural member that we're designing or analyzing. So the analogy here is we're kind of looking under the hood of that member, whether it be a beam, a column, wall, etc., and looking at what forces are acting upon that structure and how is the structure responding to those forces in the form of stress or strain criteria. So let's get started. We're going to talk about stress first, and this is interesting. This is basically the distribution of force over a cross-sectional area of a member. So there are several different types of stresses, which we'll kind of go over today, but it should be noted that given that it's a force over an area, those units are either going to be, if we're looking at metric, most of the time it's going to be pascals, which is Newton per meter squared or millimeter squared, depending on what degree of unit we're looking at. And same with imperial, with it pound per square inch psi or kip per square inch, which is just again kind of a force over an area. So for the strain, this is another way to use deformation analysis, and what we're kind of looking at here is the deformation divided by the original length. So if we have a member, let's say that's 10 feet long originally, and it deforms a foot, that strain is going to be 0.1. So strain is dimensionless because we're getting a length divided by a length. So we're having, and there's a lot of things that you can calculate using strain, which would be, the stress, there's thermal strain that you can get. You can derive actually the forces, internal forces acting upon that member through thermal expansion or contraction. And modulus of elasticity, which we'll talk about in a second, also plays a role here. And so looking at this, if we have a positive strain value, it's going to be elongated, or the force is a tensile force that's acting upon the member. Whereas if we have a negative strain value, intuitively that's going to be a compressive force, or it's going to be, shrinking. Not necessarily shrinking, but it's just going to be compressed rather than elongated. So taking a look at stress versus strain, because there's a very, very important relation here of the modulus of elasticity. So this is a general stress strain curve similar to steel. So most steel material, whatever grade, if we have A36 or A572, etc., is going to behave similarly here, where we have a linear kind of first stage. This is the elastic stage, defined by the blue elastic, in the on the top of the graph there. So we have elastic strain, meaning that the member, if unloaded, will return to its original position, kind of like a rubber band. If it's elastic by nature, so if you stretch it, but not too far, it'll return back to its original shape. So once we get to past the elastic strain point, we're going to reach a yield stress. This is defined as F sub y. This means that we have load once we pass our yield stress threshold. So let's say for A36 steel, it's 36 KSI. We go to 37 KSI. We are going to move past the elastic point to where that section is going to start to deform plastically, which means that it will not return to its original position once unloaded. So once moving on to that, we have plastic deformation. Then we have what's called strain hardening. This gets us to the F sub U value on this graph, which is where we have some plastic deformation, but the material is continuing to experience internal stress, increasing the strain. We have an increase of the stress capacity once we have reached past the yield point into the plastic hardening region. And then once we reach the extent of our strain hardening phase, we have our ultimate stress capacity. Once that is exceeded, you will experience failure, plastic failure, rupture. Just think of it as a complete failure, which is kind of when we move to the far right over here for the fracture area. That's loosely defined. Again, Claude kind of made these graphics, so it's loose. But think about it as you failed. Your member has failed. Your specimen that you're testing has failed. But we have kind of 3 points here, whether it be the elastic phase, the plastic phase on into the strain hardening, and then we have failure. So that can kind of be idealized, and same with concrete. Even though we don't get a neat curve for concrete, a linear curve for the yield point, but there are estimations to get there. So axial stress and strain is tension and compression. This is where you have a stress acting normal or perpendicular to its axis, or to its strong axis. So, or any axis really, but think of it as like a normal force or normal stress is most of the time going to be tension or compression. So this gives us a clean kind of P over A as defined at the bottom, to where we can get those KSI or PSI values. And similarly, the strain is easy to calculate because everything is acting along the same plane as the cross section. So bending stress is where we get into thinking about beam design or retaining walls. It's anything that's going to be caused by a moment. So you can kind of see it here. These graphics are kind of not very well made, but bending stress is when we have a part of the cross section that is in compression and another part that is in tension. Where the compression and tension, there is no internal force or equals zero, is defined as the neutral axis. Depending on the cross-sectional geometry, depends on the location of the neutral axis. For a perfectly square or rectangle member with an equal cross-section along the length, say you have a 10-inch deep beam, that neutral axis, again, giving constant cross-sectional area, cross-sectional geometry, more specifically, is going to have a neutral axis at 5 feet or 5 inches from the top or the bottom. This is where we get this C value as the M times C divided by I. So the M is the bending moment, the maximum, or wherever you're examining your cross section along the length of the member. So for a super technical term, it is the integration of moment, if we're looking at the entire beam, along the bounds of the length, with a length of 0 at one of the boundary conditions of the support boundary conditions, moving along the length. So you have an integration of the MC divided by I along the length. If you have a varying cross-section geometry, you'll take the integration rather than just using this formula. So the M is the moment. Again, pretty easy to calculate. It's either, if you have uniform load, you have the old WL squared over 8, or if you have a point load at the center, it's PL divided by 4. And then the C is the distance from the neutral axis to either the outermost fiber, which is where you're going to get your max bending stress, whether that be tensile or compressive. Or if you want to look at if you're looking at a composite member, for example, if you have a change in material at, 3 inches from the neutral axis, but your total member depth is 6 inches or 8 inches per se, you can take a look at any length along the neutral axis. Just know that if you're 2 inches away from the neutral axis, and you're looking at compressive stress, you're going to have the same value 2 inches on the other side for constant cross-sectional geometry of a tensile stress. So you have equal parts. And then the moment of inertia I value for a rectangular member, we know this is going to be the width times the height cubed divided by 12. This is kind of the resistance that the geometry of the member is able to provide. So a higher I value is a lower bending stress. This is an important concept to remember, as well as most of the time that the I value is a representative mostly of the height cubed. So you have a cubed value. If you increase the depth or the height of the member, think about how much resistance you're adding. You're adding resistance to the third power compared to if you were to make the member wider. So that's why a lot of times for bridges, you'll see you have a lot of moment, or some really heavy buildings, you have deep beams rather than wide beams, because you're getting more bending resistance out of that member to resist the moment. And that's a little bit more to the design side, but just kind of thinking of the inverse of bending stress, or the resistance that a member provides is going to be from that moment of inertia, really the height, in summary. So shear stress is another major stress within a cross section. This is defined as it's interesting because shear and torsional stress are pretty similar. Think about that you're kind of karate chopping a member, and so you're shearing it. So that's going to be the shear force divided by the area, or the shear flow is the shear force times the first moment of inertia divided by the second moment of inertia, or the I value, times the width of the member. So how bending stress is resisted by the height, shear stress is resisted mostly by the width, because we're multiplying the moment of inertia by the width of, so to decrease shear stress, you're going to make the section taller, because we're still getting that I value, or you can also make it wider as well. And here's a little tidbit. So for steel I-beams or W-flange shapes, or any steel member really, we're looking at shear stress is only designed to be resisted by the web of that member. So the flanges don't actually do anything if we're talking about shear stress. Steel connections. This is a shear stress is a big piece to that puzzle because bolts most of the time will fail in shear. Similar with concrete foundations, we have punching shear, one and two way shear, all kinds of fun stuff. So shear stress, while kind of confusing sometimes to visualize, um, we also will be getting a max shear stress at the neutral axis. So it's the inverse in that sense of bending stress, where it's parabolic with a max at the center or the neutral axis of that member. Torsional stress, again, very similar to a shear. Think about a shear stress, but instead of a karate chop, where it's a twisting moment about an axis of the cross section. So while similar, kind of in the failure of it, as it fails, shear and torsion fail similarly. They look similar in failure. This one is caused by a rotation. So torque, we're looking at the outer radius here, similar to bending, where we're looking at the neutral axis, the maximum length from the neutral axis. We're looking at the outer radius or the outer length of that member, and then we're dividing it by the polar moment of inertia. Polar moment of inertia is, let's say for circular rods, is going to be the diameter of that rod to the fourth power divided by 32. So to get a increase of resistance to torque, you want to make the diameter larger. For a solid circular rod. Just think about like engines, how they would behave. You have a twisting torque of a motor, for example. To resist that, you want a thicker radius or a larger radius or a thicker specimen there. So another kind of the angle of twist, as you see on the bottom right, is kind of the deflective measurement of torsion, and that is the torsional force times the length divided by the shear modulus. So here we have, like I said, torsion and shear are very, very similar. Shear modulus and then the polar moment of inertia. Again, this is kind of that resisting factor there. So the modulus of elasticity. Excuse me, this is a very, very important piece to the puzzle. So as I was saying, from the stress strain curve, modulus of elasticity is a lot derived from that in Hooke's law, which is the stress is equal to the modulus of elasticity times the strain. Here we have a graph, not to scale, I will say, but we have steel is most of the time, and this is a pretty standard number, is 29,000 KSI. If you're designing steel, obviously you're going to see that a lot. If you're designing concrete, you're going to see that a lot with rebar calculation. And there's different grades, grade 60, etc., that gives you a certain yield point. But the modulus of elasticity, 29,000 KSI, you're going to be using that a lot. And for aluminum, into kind of the mechanical side, or some aluminum structures, maybe somewhere a shed or a spaceship or an airplane, if you're into that, or kind of that niche area, is 10,000. Concrete, because it is not uniform, is you have some formulas. So we have 5.7 50. I want to say 57,000 times the square root of the compressive strength of concrete is going to be a rough estimate of the modulus of elasticity, but it is the slope of the linear portion of the stress strain curve. And again, concrete, because it's a non-homogeneous material considered, it's not, you have different areas that might have some more coarse aggregate or fine aggregate water, It's harder, which is kind of why you have that rough, squiggly equal sign, whereas steel, you know what you're getting, so we have a equals to 29,000 KSI. So modulus of elasticity, again, very important, very, very important. And you really just want to kind of almost memorize these values, but just know that it's derived from Hooke's law, which is the stress divided by the strain gives you the modulus of elasticity for the elastic region. Modulus of rupture, this is more of a concrete focused area. So it's the stress at which a beam will crack or fracture. So going back to that stress strain curve, we have that fracture kind of piece. Like I said, it's kind of a rough, estimation because we're really focusing on concrete, and concrete's funky as far as getting a strict value. So there's been numerous testing by ACI, the American Concrete Institute. In their code ACI 318, we have the modulus of rupture. This is going to be in KSI or PSI is equal to 7.5 times the square root of the compressive strength of that concrete. So this is only looking at, this is not incorporating the steel or the reinforcement of the beam or the member. It's only the concrete. And a little snippet, this is, we'll get to concrete design later, but just so you know, you want the concrete to fail before the steel. So this modulus of rupture is important because if the concrete fails, you have that visual kind of crack. If the steel fails, you can't see it because it's covered by the concrete. So you have little to no warning on, failure as far as the safety of that structure. You want the concrete to fail first, and you're designing for that. So for the FE civil exam, mechanics of materials has an entire section of about 7 to 11 questions. We're going to stress strain curve, what that relationship means, shear and moment, combined stresses. This is like axial stress and bending stress is pretty common. So that would be like a beam column or something like that. Deformations, this is deflection limits, etc. Mohr circle, this is how you would get the principal stresses of a structure, and then or of a section. And then column buckling is where we get to critical or Euler buckling loads for compressive stress of members. So that's kind of the overview of what's included in the FE exam. So actually a pretty big part of the exam. And then moving into the PE civil structural exam, mechanics of materials is kind of the bread and butter. Like I said, it's literally the engine that drives most design criteria. So we're going to have a lot of questions on it. 17 to 26 questions just on the analysis. This is using thermal deformation that I mentioned previously. As for the FE, thermal deformation, you're not going to get a whole lot of that. It's kind of what I would consider to be more advanced topic. Torsion, deflection, combined, axial, all kinds of things in the analysis section. So that's actually getting a number, and then you have your answer. For the design, we're using our mechanics and materials principles to flip that and create a design. So that's kind of why I was going over the moment of inertia, or kind of the resistance that the cross section provides for a force or a stress. Because in design, conceptually, you might have some questions of, what's the best way to reduce the bending stress on a beam? Is it to increase the width? Is it to have more of them? Is it to increase the depth? And we know that because our resistance is that moment of inertia value, we want to increase the depth if we're bending about the strong axis, of course. That's kind of the overview as far as the licensure examinations. And then moving forward to Mechanics 201, we're going to have, this is also kind of a mix of statics. So we have shear and moment diagrams, statically indeterminate structures, combined loading and principal stresses, and then Mohr circle. This is kind of going back to the principal stresses, and then buckling for the column. This is Euler buckling formula and things like that. So looking forward to the next episode. Hopefully I can get these graphics and everything kind of under control moving forward. But yeah, hope you enjoyed it. And if you have any questions, feel free to reach out, comment below what you want to see. And yeah, everybody have a good day. Thank you.